All right, hello everyone, and thank you for connecting. My name is Fabrizio. I'm the director of FORM, a research center on formal methods at the University of Southern Denmark and the Danish Institute for Advanced Study. And I'm also the lead maintainer for CSLib, which is what I'm going to talk about. It's an effort to produce a library of formalized computer science. The background that motivates CSLib is that computing is under a lot of pressure. On the one hand, we want more and more systems. We need to digitalize more things. We want more features. We want these systems to be cheaper. We also want programmers to be faster at making them. But on the other hand, especially in the past decade or so, we have met the reality that we need systems to be much more secure. We need them to be more robust, and we need them to be sustainable and be careful about the resources they consume, and we need more privacy. In other words, we need a lot of properties that ideally we would be able to prove. We would be able to use formal methods to reason about the systems, but the infrastructure for formal methods is just not there yet to be adoptable on the scale that the world would need. So in 2025, we actually started a couple of parallel projects behind the same idea. So we decided to get together to coordinate efforts, and that's how CSLib came to be. So CSLib is an effort, it's a project to build the necessary infrastructure to scale up the formalization of computer science results and the way we do programming based on formal methods. In concrete words, it is an open source project. You can find it at that link. It contains computer science definitions and results. It contains verified software components that we hope people will be able to take off the shelf. And we are building a verification infrastructure for new and old code written in a variety of languages. And we have just started, so a lot of the things are still missing, but I'm going to talk a lot about what we have already done. CSLib is written in Lean with Mathlib as a dependency. Mathlib has been a fantastic enabler for our efforts. It's curated by experts, and it's done in collaboration with the Lean community and the FRO. So you can find us on the CSLib of the Lean community. CSLib is backed by a steering group where we worry about the long-term strategy and procuring funding for the initiative, a maintainer group that worries about the technical leadership and supervision of the project, and a lot of discussions among its contributors that are too many to list and present here. So I encourage you to go and visit the GitHub repository to get an overview. We mostly discuss on Zulip and GitHub, but also emails and other channels. This lib is for different kinds of people. So we hope that researchers, especially in computing, will use it in the future to verify their claims, and even will start thinking that it's worth to start being formal from the get-go of new projects once the library is mature enough. And we also hope that they will upstream some of their findings if they are of interest to the wide community. It's also for educators because they will be able to explore together with their students computer science through a unified language, which is going to be Lean, and interact with it through the Lean development environment. We are going to reach out to the programming community. Hopefully they will use our components to write reliable software, but also our languages and logics to check their system models and their assumptions and their implementations, and also our verification infrastructure to verify the new code and the old code that they have. We also have AI developers because the idea is that by training AI on CSLib, just like good AI has been trained on Mathlib, will increase the good and useful production of specifications, programs, and proofs that these programs actually respect the specifications by AI, so to enable more trustworthy AI in the future regarding programming. And last but not least, we are reaching out to interdisciplinary researchers also in other disciplines like social science, because there are some prototypes and pilot projects that are exploring the application of formal methods to provide actionable information to users such that they can make well-informed decisions based on the properties that the systems provide. Now I'm going to give you a brief overview of where we are now, and everything I'm going to show, the credit goes to the contributors that you can see at the link on GitHub. The current structure that you will find in our repository has these directories currently. So you will find some general reusable foundations that cut across all the topics in computer science, languages for modeling and programming systems, logics for reasoning about different kinds of properties, and then more area-specific directories like algorithms and computability, where we go deep into one direction. We have found many answers by exploring these things, but of course, most of the interesting questions still lie ahead. But let me give you some examples of what we already have. So in foundations, you will find the transition systems with their classification. And notably, we already have quite a few notions of equivalences between transition systems, like bisimilarity, trace equivalence, and so forth. We also have reduction systems, and this pushed us to defining some general notions regarding relations, like what it means to have a confluent relation. And we have the Fourier monads to program effectful computation. Now, one of the things that we evolved into quite quickly is adopting what I call the grind first approach. I'm just going to give you an example, but to see more of this, you should watch Chris Hansen's talk tomorrow, where he's going to go deeper into this. But grind has been a fantastic ally. A lot of our proofs are becoming a single invocation to grind. We have started using grind so greedily that basically when grind can't do something, we become suspicious of our own design. And when grind can't do something and we are sure of our design, that gives valuable feedback to the developers of grind. We are trying to keep this up because I think that to have such a big development and to actually sell to programmers in general in the future that they are supposed to do this kind of stuff, then tools like grind are really essential. In the languages directory, you will find the lambda calculus actually in different forms. So we have both the untyped and the typed variants, some of them at least. And this is because they merit to be distinct from a theoretical viewpoint. But then there's another interesting aspect, which is that when you formalize the lambda calculus, you have to worry about how you formalize alpha equivalence, or the notion of binders, if you like. Because what people use in pen and paper presentations is very inconvenient and cumbersome when you do formalization. So we currently have the pen and paper technique, but also some alternatives that are easier to formalize. That's what people typically do. And we hope to establish that you can switch between these different kinds of presentations such that you can always use the most convenient depending on what you're trying to do. We also have CCS, which is one of the most well-established models of concurrency in concurrency theory. And most notably, we have already proven a substitution principle, which is a cornerstone of concurrency theory. Basically, that if you take a little piece of code and you replace it with a bisimilar or equivalent piece of code, you can always do that and it's sound without worrying about the context. And we also have combinatory logic and the first proof of Rice's theorem. The lessons we got here is that there are a lot of interesting reusable APIs that we can develop if we worry about generality, which we do. And Chris is going to talk more about this. One example that we have is that we saw the problem of getting a fresh variable. So you have a term in some language that mentions a bunch of variables, and now you want a fresh one. And this happens so often that we made a class for it. And there's even a tactic that gets one for you by looking at the context you currently have in your proof. In the logics directory, mostly now we have linear logic so far. We have the sequent calculus, we have many logical equivalences, we have proven eta expansion correct, we have a phase semantics, but we don't have, there's a lot of work in progress, but there's a lot of interesting, there are a lot of interesting aspects regarding the design of logics. So we are trying to be very careful with getting it right, or at least getting it almost right. Another thing that is slowing down the development in logic is that you have to deal with proofs that typically on paper you end up proving that you have reached the right conclusion. The conclusions are typically modeled in terms of multisets or sets or whatever it is. And to convince Lean that you have actually reached the right conclusion is somewhat challenging sometimes because it's a lot of multiset rewriting. Here's a very simple one that I had to prove recently. And if I didn't have grind, I would waste, I guess, at least 80% of my time just with the silly rewritings, right? So what we have is we're accumulating a database of grind patterns for this kind of rewritings, and then we pray to the grind gods that that we can get grind to do the heavy lifting for us, and then we have to deal with this kind of stuff. In the automata directory, you will find deterministic and non-deterministic automata, and we have a theory of acceptors for finite and infinite words. What is interesting here is that there's been a lot of interaction between the theory of transition systems and that of automata. In particular, we have taken a lot of care to design automata theory by extending the theory of transition systems. So a non-deterministic automaton in CSLib is a transition system equipped with a set of initial states. And then based on that, you can extend it further with whatever acceptance condition the kind of automaton you're dealing with now requires. So that's the one for typical acceptors of finite words. This is the one for Müller automata, for example. And since they all share the same infrastructure from the transition system module, proving a lot of things that are of interest in this domain can just be done with a call to grind. So for example, when you do the usual translation of non-deterministic automata into deterministic automata, that's based on the usual notion of images for transition systems, and so it can reuse all the theorems we have about that. When you do the encoding from epsilon NFAs to normal NFAs, so from epsilon non-deterministic automaton to non-deterministic automata, well, that's based on the notion of saturation of a transition system, on which we have a lot of results as well. So that's also a very simple proof. And this also pushed us to generalizing a lot of results on finite and infinite executions about transition systems. So they influenced each other in both directions, transition systems and automata, and both are better because of it. Then we have algorithms. What you will find now is a very lightweight framework. We are just beginning for writing algorithms and proving their time complexity in terms of atomic operations. We have merge sort proven correct with its time complexity. People are also working on alternative models for doing this, and we also need to gain a lot more experience by writing a lot more algorithms. Also, there are a lot more properties than just time complexity to worry about. One observation I have to share here is that it seems to me that one of the most important concerns is balancing robustness of the approach with its ergonomics. For example, with the lightweight framework we have now, you write the merge function as found in merge sort, basically as you would normally write lean code, which is a very good thing. We want to be user-friendly in that way. And then we have a proof of its time complexity. But this approach relies on the user adding a little annotation as to the atomic operations that should be counted when you do the proof of time complexity. Now, if you get these manual annotations wrong, then your theorem is inadequate, right? It doesn't mean much, or it's misleading even. So we are investigating a lot of different alternatives that either make these annotations more robust, or it doesn't require annotations. They are automatically picked from a database, or we change the approach such that the annotations are in a trusted separate module. In any case, the concern is always it should be easy and ergonomic, but it should be as precise as possible. What's coming next? Well, almost everything. There's a lot more to computer science than what I've shown you. So just to give you some examples, very incomplete by necessity, we still haven't looked at database theory. I would love for some people to start making contributions related to it. In the area of semantics, we still lack probabilistic semantics, denotational semantics, lots of stuff. A lot of the things in concurrency theory that are very useful in practice, but also in theory, to reason about the expressivity or to model concurrent behavior in machines is not there yet. We also plan on introducing choreographic languages at some point because this would allow us to model security protocols, program distributed systems with choreographic programming, model business processes, do multi-party session types that are used to type concurrent and distributed programs, etc. We have a lot of logics that we miss. I'm looking forward especially to modal logics, separation logic to reason about shared state, but there are also many more that are of wide interest, and so on and so forth. We need to work hard on our verification infrastructure. In particular, we're working on the development of intermediate representations that people can share for software verification, especially the one called Bool. Currently, you can find a lot of examples in a separate branch from main. We will develop compilers from mainstream languages to Bool. And we also want to integrate logics with the verification infrastructure, because in general, you might be interested in proving all different kinds of properties about the software you're dealing with, from temporal to spatial and so on and so forth. And finally, I'm looking forward to seeing a more programming infrastructure built with CSLib. In particular, the design and implementation of new languages that come with certified compilers. And I would like to also see if we can bridge this way of doing things to the way people normally do software engineering. So by formalizing, for example, design patterns and write provably correct code transformers that apply refactorings to code that come with strong properties about the result. And last but not least, again, I think it's going to be important to integrate what we do with middleware out there, such that people can write code or model systems in CSLib and then deploy it in modern software architectures like microservices as found in cloud computing, serverless, and so on and so forth. And that's it for what I had. I thank everybody who's contributed so far for all their work. Thank you very much, and thank you for listening. And if there are any questions, I'm happy to take them.
Thank you very much, Fabrizio.